This chapter, you're going to learn how the empirical relationships between two variables is affected by random sampling error. It's a familiar theme of randomness applied. How to use an informal test in making inferences about relationships. Or how to use more formal statistical tests in making inferences about relationships. So we're going to look at both of these angles. How measures of association gauge the strength of an empirical relationship. And which measure of association to use in performing and interpreting political analysis. What's the difference between a test of significance and a measure of association? Well, a test of statistical significance, which in my opinion is probably the more important of these two elements. A test of statistical significance helps you decide whether an observed relationship to an independent-dependent variable, that is the relationship you're observing in a sample, really exists in the population, or whether it could have happened by chance when the sample was drawn. So the face-off here, the tension, is between what you're observing in your sample and what is going on in the population. Could what you have in your sample reflect what's going on in the population? A measure of association tells the researcher how well the independent variable works in explaining the dependent variable. So both these aspects of statistics come into play when you're trying to assess the significance but also the substantive strength of empirical relationships. Let's look first at statistical significance. And let's just take an example. These numbers are very close to the real numbers in the American National Election Study 2012. Suppose we have the American National Election Study and we calculate the mean Democratic rating among female and males in the sample. So we split the overall sample into two groups on the basis of the independent variable, gender, and we calculate a female mean rating of the Democratic Party at 54 degrees and a male mean of 49 degrees. So we have a 5-degree difference between males and females. Here's the question, and this question ought to be increasingly familiar given the topics that were covered in Chapter 6. Can we infer that in the population from which the sample was drawn, that females do, in fact, rate the Democratic Party higher than do males? So that's the core question that we're asking, not unlike the inferential questions that were asked in Chapter 6 about a single population mean. Now let's apply this standard in a couple of ways here. The first way you're familiar with. I mean, suppose we have a female mean, sample mean, we have a male sample mean. We would compute the confidence interval, the 95% CIs for each mean, and compare those CIs. I mean, obviously, if the two 95s do not overlap, we can reject the null hypothesis, and if they do overlap, however, we cannot reject the null hypothesis. Compare the 95% CI of two or more sample means. If the intervals overlap, then we cannot reject the null hypothesis. And the reasoning here is you get a sample mean that's a point estimate, but we know around that point estimate is an interval of confidence. It could be anywhere within that 95% CI. And if those two CIs overlap, then the two population mean could co-occur in the population. If they do not overlap, if there's distance between the 95% CIs, then we can reject the null hypothesis. And here's the example in the book. Again, we have over here the female mean 54.1 on the thermometer scale, the male mean 49.1. Instead of computing the difference, we're getting to that. That's the next approach. Simply compute the 95% confidence interval of the female mean, and just in the way we're familiar with, you would take the standard deviation and divide it by the square root of n. That would give you the standard error of the female mean. You could multiply that times 2, add it to the sample mean, subtract that value from the sample mean, and we would come up with the 95% CI over here. So what we can say is that in the population from which the sample was drawn, the lowest plausible value for the female mean in the population is 53.1, and the highest plausible value is 55.1. Any claim within that range cannot be rejected. Every proposed population mean in that interval is plausible by this definition. Do the same for the male mean. 49.1 figure out the standard error of the sample mean, multiply that by 2, and add it to 49.1 for 50.1, and subtract it 48.1. So the inferential question here is, does the lowest plausible female mean, 53.1, overlap the range of the possible male means? Well, the highest plausible male mean is 50.1, so these two plausible limits do not overlap. I'll just show you the math, or make this point reemphasize. The female mean is 54.1, standard error of 0.52. The lower confidence boundary, therefore, is 53.1. The higher confidence boundary is 55.1. Do the same for the males. The lowest 95 CI boundary is 48.1. The upper is 50.1. So the most plausible, the highest plausible mean for men is 50.1. The lowest plausible mean for women is 53.1, and they do not overlap. This is what's called an error bar chart. Here's the female mean, there's the sample mean, and here's that bandwidth of confidence. It could be as low as the lower hinge here, but way down here there's the male sample mean, and there's the highest plausible. Was it 50.1, I think? So all this white distance between these two confidence interval brackets, it represents a very low probability territory. And there's an extraordinarily low, we'll see how low in a minute, extraordinarily low probability that in the population the two means came from the same population. And so we would have confidence in saying, well, inside the population, yes, females do give the Democratic Party higher ratings than do males. We just looked at the confidence interval approach to testing for the difference between two sample means, and it's, again, like all CI approaches, it's durable. It won't lead you in the wrong direction, but it does lack precision. A more precise way to test for differences between two sample means is the probability value, or the p-value approach. The idea here is to determine the exact probability of obtaining the observed sample difference, so we're going to focus on the difference now, under the assumption that the null hypothesis is correct. So again, the hypothesis testing logic is the same, but now we're going to focus on, instead of the two means and their CIs, we're going to focus on the difference between the means. The p-value approach is based on obtaining and evaluating the standard error of the difference between two sample means. And here's the table again. There's 54.1 for the female mean, 49.1 for the male mean. In this case, we're going to work with this difference of 5 units on this feeling thermometer scale. And so what we're after is the standard error of this difference, and just see how much of this 5, just how much error is there in that 5. How big could the difference be in the population? How small could the difference be in the population? Here's the process. We take the standard errors of each mean, and we square them over here. So the female mean, 0.52, is the standard error. We square it, 0.27. The male mean, the standard error is 0.53. We square that, we get 0.28. We add those two numbers, we sum them, get 0.55, and then we derive the square root of this 0.55 and arrive at the standard error of the mean difference, which is 0.74. Let's review those steps quickly, and then we'll see how we apply it. What was just done? 1. Square each mean standard error. The square of the female mean standard error is equal to 0.27. The square of the male mean standard error is equal to 0.28. Sum these squared standard errors. In the example, 0.27 plus 0.28 is 0.55. Take the square root of the sum obtained in the earlier step, which is equal to 0.74. So the square root of 0.55 is equal to 0.74. That is the standard error of the difference. Now the so what question. We obtain a test statistic, and what we're going to do, we're going to convert the difference asserted by the null hypothesis here, which is always 0, because that's the null hypothesis' favorite number, and the difference we obtain in the sample, which is represented by the alternative hypothesis, which is 5 in the current example. That gives us a z statistic. Divide that difference by the standard error of the difference to standardize that difference. See how many standard errors those two numbers are apart. The same test statistic, of course, can be computed for the t statistic. It's the same math. The distribution for t, as you know from the previous chapter, is different from z, but for large values of n, the two distributions are very similar. In both cases, the test statistic is 6.8. Now, what does this mean? This means that the null hypotheses asserted difference or hypothesized difference of 0 and the observed difference of 5 are 6.8 standard errors apart. Imagine the standardized conversion of a normal distribution where z of 0 is on the mean, and then you go out 1 standard error in either direction, 2 standard errors, 3 standard errors. You know how thin the curve gets, how rarefied it gets when you get beyond, 3 standard errors. The probability of those events out there are very rare. So imagine standing at 0 and looking down almost 7 standard errors into the frontier of the normal curve, and you get an idea just how remote the probability is that random processes produced a mean difference of 5. If in the population the mean difference between females and males is equal to 0, as asserted by the null hypothesis, how often by chance will we obtain a difference that's 6.8 standard errors from 0? And I had to ask Stata, a data analysis software, to return a probability. It's always a non-zero probability, but in this case the answer is about 400 times out of a billion. So if the null hypothesis is correct, and that chance processes produced this difference of 5 that we saw between the female and the male mean, that process would produce what we saw, an extremely fluky outcome 400 times out of a billion. Reject the null hypothesis.